All right, so this comes from ACE 9702, paper 23 from May, June 2014, just like you have like your weekly quizzes. This is just a practice problem. We do that and initially wants us to explain what is meant by a scalar quantity and by a vector quantity. We've done that before. I'm not going to take the time right now to write all that down, but I will remind you all that scalars are quantities which have magnitude only, and vectors are those quantities which have magnitude and direction, something that we've talked a lot about. Now it goes on to read, a ball leaves 20 feet at the top of a cliff with a horizontal velocity of 50 meters per second as shown. That's the sideways velocity, right? Horizontal velocity. It says the height of the cliff is 25 meters. The ball hits the ground at point Q. Air resistance is negligible. Calculate the vertical velocity of the ball just before it makes impact with the ground at Q. So as this ball falls, gravity is going to accelerate it. It's going to make it pick up some in a downward direction. It keeps the 15 meter per second sort of sideways vector all the way throughout its motion. So like gravity doesn't slow this down, so it's still going 15 meters per second that way, but we're just solving for how fast is it moving downward by the time it hits the ground. Let's think about the essential question over there, and in particular, the utilizing the equations of uniformly accelerated motion part of it. So once we've derived them, we can use them. We don't have to derive them every time we want to use the equation. Let's think about what they are. V equals U plus AT. Well, we don't know how long it's going to take to hit the ground, right? They didn't tell us how much time. In fact, it's what they asked us to calculate next. Like maybe we could do that first and then we know it and we could solve this one, but since we don't know the time, let's keep on going through our equations here. S equals UT plus 1/2 AT squared. Once again, we don't know the time that it's going to take to fall, so we wouldn't be able to solve for the final velocity. Also because final velocity doesn't show up in this equation, so kind of hard to solve for that if it's not there. The other equation with displacement is this one, and now we do have final velocity, but still that time variable is something we don't know. So all three of these equations are no help until we know how long it's going to take something to fall. Really the only equation that we'd be able to use to solve this one without calculating the time first would be equation number 4, which says the final velocity, the thing we want to know, squared is equal to the initial velocity plus twice the acceleration times the displacement. We know the displacement is 25 meters. They give us that. The acceleration here, the question isn't friendly enough to remind you that we can assume this is here on Earth, where the acceleration due to gravity is negative 9.81 meters per second squared. So we do know the acceleration. You as a student of physics have to know that that's the acceleration that we're using. If it's a cliff, they don't tell us it's a cliff on Mars, or the cliffs on Mercury are actually some of the steepest in the whole solar system because Mercury's core probably cooled, and then so like the crust like sort of collapsed in, so very steep cliffs on Mercury. Some of the moons of Uranus also have those cliffs. All right, so this will be the equation that we'll use here. Everything is dimension, independent, so just the y component. Everything that's a vector here is just the y component, okay? The displacement is the y direction, the acceleration is that of gravity only acting in the y. What is the initial velocity in the y direction? Exactly, 0. Everybody was quiet and didn't say anything because you all know that the initial velocity in the y direction is 0. It's only moving sideways initially. So we can solve for v sub y like this. V sub y squared plus 2as. And I'm actually solving for this, so I'll just leave it on that side of the equation. V sub y squared equals 0, because the initial velocity in the y direction is 0, plus 2 times negative 9.81 times 25 meters. Now, if I go to solve this, and that negative sign really bothers you, and you're like, I can't take the square root of a negative number, just make this also negative. It's falling down. We're going down 25 meters, then you multiply those two, you get a positive. Now we're good again. So sometimes it's really important to keep track of the sign convention. In this one, we can just kind of assign this one as negative. Like it makes sense, it's falling down, down is negative. If I make this negative, gravity always acts down. It really is important for like projectile motion calculations, like on the chalkboard over there, where we're launching at a non-zero speed, a positive speed up. Then we really do have to keep track that gravity is negative relative to it. So whenever vectors oppose each other, that's when it's really important. know, when one is negative relative to another one. These ones are both in the same direction, so they're either both positive or they're both negative. It's up to us to sort of decide. And then that's a very solvable question, right? So we're going to have here 2 times 9.81 times 0.5. And so we get the velocity in the y direction squared equal to 490.5. So the square root of that. Oh, that's not right. 25 times 9.81 times why is not taking it out? Here I am taking a cube root like an amateur. All right, 22 meters per second, I'm good. Are you guys getting that? Is anybody else like, you lost me back, on the bell ring? All right. So this equation will allow you to get to that answer without having to know how long it's going to take something to fall. If you look at the equation that says h equals 1/2 gt squared, it comes from this general equation of motion. If something's just falling, like here, it's not traveling with any initial velocity in the y direction. So like we could think about equation 2 here and go, oh, the first term will go away if something's just dropped, just falling. We don't throw it down with any, you know, positive velocity. So there we can think about the displacement s as being vertical. So I'm going to call it the height. Okay. So I'm using this equation 2 here to get a sort of a special case type equation. When things are falling from a given height in a gravity field, we'll write it like this. The displacement s is h for height. If we're dropping it, then this term goes away, right? The initial velocity is 0. So I just have the 1/2 at squared. Well, if the acceleration is that due to gravity, called lowercase g, and so this is a nice little equation that relates the height of something falling in a gravity field and how long it's going to take to fall, right? It relates the height and the time, and it goes as the time squared, okay? It comes from the more general equation, like I said up here, but it's a useful one to just have at your disposal in terms of like you have a list of equations. I would have this one written like this, you know, h equals 1/2 gt squared, because it's such a typical problem like this where we know how high up something is, or we can deduce how high up something is because we know Earth is 9.81 and we can time how long it takes to fall. This is why it's kind of useful. You learn physics and you're up on a really tall bridge and you're like, I wonder how high up we are. I'm going to drop, you know, a rock or something, time how long it takes to hit the ground, square it, multiply it by 9.81, divide it by 2. That's how high up we are. Here's your bonus lab work for this week, because I know everybody is just, you know, clamoring for some bonus lab work. But like, now that we found the acceleration due to gravity with the pendulum, how can we use it, you know, with something else that's interesting? So I challenge you all to drop something from the greatest height that you can safely get to and time how long it takes to hit the ground safely. Safety first, you guys. So if you time it, if you drop something and you time it, how long it takes to hit the ground, you know now how to calculate how high up you are just based on that time. You're in Earth's gravity field. No one did this experiment anywhere besides the surface of Earth, okay? No, wait, I take that back. If you have the means to go to the moon or Mars or any other gravity field, do so, okay? That's probably an assignment for like future business classes once we kind of get there, the commercial space flights, right at the dawn of the space age here, folks. Time to be like. So probably Earth's gravity field for most of us, okay, unless you're very resourceful and clever. Time it, square it, 9.81 divided by 2. That's how high up you are in meters, right? Because this is meters per second squared. You can always convert it to feet if you wanted a more familiar unit. Wow, 15 meters, is that tall? You know, less than you could drop a tennis ball off of the 37 balcony, right? Time it, hits the ground, safe, it's not gonna hurt anybody, make sure it's clear there. You don't need to, you know, drop by an errant tennis ball in the head as you walk underneath the 37, you know, stairwell. Some of you might be able to get to even greater heights. Confident that some of you will. Keep safety first in mind, okay? Don't go anywhere where, you know, I mean, there's lots of gravitational potential energy at those heights, okay? We'll study energy. Energy can either be created or destroyed. You give yourself that potential energy, okay? Earth's gravity field could convert it into kinetic energy of motion, like you can fall, you know, so really do be safe about this. And by the way, it's an optional lab. You don't have to do it if you don't want to. If you're interested to go like, yeah, I want to know how tall up my, ooh, what if you did this? Then we have a trampoline at home? Am I the only one? Okay. So it's like you could like, as high as you could get to on your trampoline or then drop something there, you know, then see like how high up can you reach on your trampoline or something like that. Anyway, let's finish the calculation here. Show that the time taken for the ball to fall is 2.3 seconds. So 25 meters equals 1/2 9.81 meters per second squared times the time squared. And so you're simply just solving that for t, right? Because we're given the height and we know that we're on Earth. So if we solve that, t equals 2 times 25 divided by 9.81. Some students will just like to like crunch these numbers now and then do the algebra. You could just do the algebra and sort of see what it's going to look like in the calculus. Like multiply both sides by 2, you get rid of the half. Divide both sides by 9.81, get rid of that, and then take the square root and you've isolated t. You can type that in your calculator. 50 divided by 9.81, 5.05, and the square root of that is 2.2. So here you're saying t equals 2.25, which is indeed about 2.3 seconds. Remember when it says show that something is a given value, you want to actually do the working. You don't want to just write the number that is the answer down like, there, I showed you. So that's not good working, writing the answer down. This is what we want here, this kind of physics going on here. Like, oh, okay, I'll show you, there. I don't need to show you, you told me. Like prove, you know, might be a good verb there. Prove that the time that it takes is. Mindful that I'm recording.